to it using a bit of JavaScript. And so everything that BFS breadth first search has explored so far is in green on the maze. And we can see that it kind of flows through the maze like water. And this is what I mean by kind of layered by layered approach. So every time we hit a fork in the maze, we go out and we explore all paths going out from that. One of the really nice features of BFS is that once we've fully applied it and fully explored the graph, we can then use it to find the optimal shortest path between 2 points. So for a maze, that's useful because we can put the start and the end and actually find the solution to the maze, the best solution to the maze. So that's one application. So other obvious applications would be stuff like GPS navigation. But it's actually a very fundamental algorithm and is used everywhere. From things like optimization problems to model checking to even things like drug discovery, where you have a graph of the different interactions between proteins, so a model of a cell, and you're trying to figure out which chemicals disrupt that. And you will use breadth first search to actually analyze that. So the point I'm trying to make is that it's a very fundamental algorithm, and it's really one that you should have in your tool belt. For this reason, it's often used as an interview question in big tech companies. So that's another good reason to learn it. So in this lecture, we're going to look at breadth first search, BFS. I'll start with the first 15 minutes by just trying to give you a real intuition for the algorithm. So there won't be any pseudocode or set theory. We're just going to look at kind of visual examples of it to really try and give you an intuition. The next 15 minutes then, we're going to do an in-class problem to kind of cement that. And then finally, the remaining of the time, we'll start looking at some pseudocode and how you might actually implement this. And that'll also be set as part of your problem sheet. As always, all the slides are interactive. And so you can go to the course webpage and go on this page. And step through the slide deck, and you can change kind of the graphs and step through them slowly. They'll all be implementing the algorithm. So I mentioned that breadth first search it goes through and explores the graph in a layer by layer fashion, but I just really want to illustrate that. So here we have a directed graph. It's a tree. So remember last lecture we talked about directed and undirected graphs. So a directed one is one where the edges have a particular direction, so we can only traverse them in that direction. And so this is a directed graph. You can see there's arrows on the edges. And I'm just going to select, so with BFS you select a starting node. So in this case I'm going to select the root. And how the algorithm starts off is it looks at everything that is immediately accessible from the starting node. So in this case, we have 2 nodes that are immediately accessible via these 2 edges. And so it queues those up, and it queues them up and in order to visit them later. So it starts off, it queues up these 2, and then at the next step, those 2 will become the active node, and then everything on the layer below, so everything that's accessible from the current active nodes will be queued up next, and so on. So we step through until we visit the entire graph. This works equally well for undirected graphs. So here we have a very similar graph to the previous one, but now it's just laid out a bit differently and the edges no longer have a direction. So an undirected graph, remember from last lecture, you can go in either direction between 2 nodes. It just connects them. And so I'm going to set 14 as our starting node, and we step through. So the only accessible node from 14 is 5, so that gets queued up. Then 5 becomes the active node, and we queue up 16, 15, 17, and 2. But importantly, we don't queue up 14. So remember, this is an undirected graph. So 14 is accessible from 5, but we don't queue it up. And so this is another consideration of BFS, is that we're going layer by layer through the graph, but we're only visiting each node once. So at the next step, 16, 15, 17, and 2 become the active nodes, and we queue up 6, 1, and 4, but we don't queue up 5. We've already visited it. So BFS, we're going layer by layer, but we're only visiting each node once. So if I step through the rest of this, okay. Again, this is the same thing, but just a different graph. So we have a star graph here, starting at node 5, and stepping out, you can see it kind of sweeps out, exploring every single node in a layer by layer fashion. So how do we actually do this layered by layer kind of exploration of the graph? To do it, we use a data structure known as a queue. So a queue is much like a queue in real life. So say you go to the bank and it's a bit busy and you join the back of a hopefully socially distanced queue. And whenever a teller becomes available, then the person who's at the front of the queue will leave the queue to go to that teller, and everyone else shuffles forwards. So that's the same here, but instead of people, we are using it for nodes that we want to explore. So we go through, and for each node that we're examining, we look at all of its neighbors, and we enqueue them at the back of the queue. So that enqueue is the term that we say for putting it to the back of the queue. Once we've explored all the neighbors, we then look at the front of the queue, find out which node is queued there, and then that becomes the active node. So we dequeue that. That's what that term is. Dequeuing is taking the item from the front of the queue. Okay, so let's go through and see how we can use this queue to actually apply, to actually implement BFS on the graph that I just showed you. So here we have that graph, and down here you can see we have our queue. At the moment there's nothing in it. So I'll select 5 as our starting node. And so the first thing that the algorithm does is it looks at all the immediate neighbors of 5. In this case, it'll be 1, 4, and 10. And it walks through them, enqueuing them, so putting them into that queue. So first one up is 1, so we enqueue that. Then the next one up is 4, we enqueue that. And then finally 10, we enqueue that. Now we've explored all the immediate neighbors of 5, so we're kind of done with it. So we look at the top of the queue, the front of the queue, sorry, and in this case it's 1, and we dequeue that to make it the active node. So 5's been marked as kind of fully explored, and 1 has become our active node. Now in a similar fashion, we grab all the immediately accessible neighbors of 1, and we examine them. So 2, we enqueue that, and now we reach 5. But we've already explored 5. And remember I said that we're going layer by layer with BFS, but we're never revisiting a node. So in this case, we've visited 5. We don't need to queue it. So we don't queue it here. Next one is 6. We haven't visited 6, so we enqueue that. And then we pop off the front of the queue for 4. 3 hasn't been visited, so we enqueue it. 5 has already been visited. We don't enqueue that. 9 hasn't been visited, so we enqueue it. Pop off 10. DQ 10, sorry, I keep saying pop off. DQ 10. 5 is the only immediately accessible neighbor of 10. We've already visited it, so we don't need to enqueue it. DQ 2. Now, we've already explored 1. 3. We haven't fully explored 3, but 3 is already in the queue. And we count this as visited, so we don't enqueue 3. 7, we haven't visited 7 or queued 7, so we enqueue that. And then I'm just going to kind of quickly go through the rest of it. We keep doing this, enqueuing and dequeuing, until we fully explore the graph. And in essence, that is it. That is breadth first search. We explore the graph layer by layer using this queue in this fashion. And so if we look at that tree example I showed again, it's doing the same thing. It visits all the immediate neighbors and queues them up and then dequeues them once it's explored all the neighbors. But one thing I want to show with this tree is that as we start to get down towards the leaves of the tree, we can notice that this queue actually starts to get quite big. So we can see it's really starting to grow now as we queue more and more nodes that we want to consider later on. And this is a very important consideration with breadth first search. So it's a great algorithm. We can use it to find the optimal shortest path. But if we have particular input graphs, then we can actually end up with quite a big memory problem. So the space complexity can be quite large. And so that's something that we really need to consider. And to kind of illustrate this a bit more, I have another example, which is up here. Or another 2 examples. And these are graphs that I have used a Python script to generate. And they have the same number of nodes and edges, but each one will have one thing that's kind of changed, which I call a locality factor. And that's kind of how localized the connections are. So there'll be 2 graphs, one where the connections are very localized, which is this one. So you can see it's actually a ring. So all the edges are reasonably close together. There's no big kind of arcing edges across the whole graph. As the next one will have a high locality factor. where it'll look much more like a bowl. And so if I actually play this, so because this has a low locality factor, we can see that, the algorithm kind of slowly sweeps through. But that queue doesn't get unmanageable. It's staying fairly small as BFS kind of sweeps around it. But if we go to the next graph, which, I generated this with the same script, same number of nodes, same number of edges, just that locality factor has been changed. And so, the connections can be can span a larger distance. Then when we play this one, we can see that queue grows considerably faster and becomes quite big. So BFS is a great algorithm, and we can use it to find the shortest path, as I will get onto showing you. But we need to be, and we're using a queue to kind of go layer by layer, but we need to be quite careful with this queue and consider the input graph and how that can kind of affect our memory usage. There will be another algorithm that we will look at later on in the course, something called iterative deepening, which has the same benefits of BFS, so for finding the shortest path, but it doesn't have the same space complexity. But yeah, we'll get onto that later. Okay, so we've got BFS where we can explore the entire graph in this layer by layer fashion, but how do we actually use that to find the shortest path? To do that, we need something extra on top of what we already know. We need something called a parent array. The parent array just kind of keeps track of how BFS kind of traverses the graph. And so the parent array, it's an array that is the same size as the number of nodes in the graph. So for every node in the graph, there's an element of the parent array. So here we have an example graph which has 7 nodes, and so we have 7 elements in our parent array, 1 for each node. And basically what we do is whenever during BFS we enqueue a node, we keep track in this array the active node when we enqueued it. Okay, and then once we've explored the entire graph, we can then use that information to kind of go backwards to find the shortest path. Don't worry if that wasn't completely clear. It will become a lot clearer once we go through an example, which I'm going to do now. So we've got this graph here, and I'm going to set a starting node and an end node. And so we want to compute the shortest path between these two nodes. And so that's instantly obvious to us, right? So we go down the left-hand side. We go through 2, from 1 through 2 down to 7. We wouldn't want to go this way where we have to go through 3, 4, 5, 6 down to 7, right? So hopefully our algorithm should tell us that this is the shortest path. And now I'm going to step through. Okay, so the first step is we look at all the accessible nodes from 1. So that's 2 and 3, and we enqueue them. So we enqueue 2, and we can see that in the parent array, at element 2, we enqueued the current active node. So in this case, it was 1. So here in location 2, we put 1. And then similarly for 3, when we enqueue that, we put 1 in there also. Now at the next step of the algorithm, we dequeue. 2 is now the active node, and we're going to be enqueuing 7. So in location 7, we now enqueue 2, because 2 is the active node. Okay. Then we dequeue 3. So now when we step through here, 4 is being enqueued. And so in location 4, we add 3. And then similarly for down the right-hand path of the graph until we've explored every node in the graph. Right. So we applied BFS, and we had this parent array where we're tracking kind of where we're coming from every time we're going. How do we use this to compute the shortest path? Well, we start by looking at the end node. So we kind of go backwards to build the path. So we're kind of constructing it in a backwards fashion. And so the end node here is 7. So we go to our parent array and we look up 7. For location element 7, we look up where we actually enqueued 7 from. And so in this case, it's 2. Oh, sorry, I need to stop again. So in this case, it's 2. And so that becomes kind of the last stage of our shortest path. So we add this to our path. And then we go to 2, and we look up where that got added to the parent array. And in that case, it's 1. And then at 1, we're in the parent array, it's null, because that was our starting node, or our starting node. And so we know that we found our shortest path. So This is a really nice feature of BFS. You just kind of explore the graph, and then by tracking this, kind of the optimal shortest path just kind of falls out of it. It's really quite neat. Yeah, and so that's how we do it. We just walk backwards through this parent array. And so going back to our example of a maze, how we do the same thing here. So we just have so how I do it is for the maze, I turn this into a graph, and I don't turn it into an optimal graph, but basically what I do is for every cell in the maze, I create a node in my graph. And then if you can move from one cell to another, I add an edge. And so the lack of an edge symbolizes a wall in the maze. And we do the same thing. So we walk, we apply BFS to our graph version of the maze, enqueuing neighboring adjacent cells, and then dequeuing them, and adding things to the parent array. And then once we've explored the entire maze, which will happen any second now, we then walk backwards through our parent array, finding the shortest path out of the maze. And if we just check, yeah, that is definitely the shortest path, because if we went this way, that's a lot longer, right? Yeah. Cool. Okay, so, and of course then, so you can see the parent array down here. And you can step through this at a slower rate offline to get more of a feel for it. And of course then we can scale this up and apply it to larger mazes, such as what we had in the title slide. So that's BFS. I hope you've got a good intuition for it now. So we're exploring a graph, visiting every single node, only visiting every single node once, in a layer by layer fashion. We're using a queue to do this. We need to be a bit careful about the input graph if this queue becomes unmanageable or not. And then we can actually find the optimal shortest path between 2 points by using a parent array and keeping track of that. So the rest of the lecture, we're going to do a pen and paper exercise just to try and reinforce this. And feel free to kind of mess about with the slides and play about with them. And then the remaining time then we'll look at some pseudocode and how you might actually implement this with things like an adjacency list and a little bit of set theory. I'll try and formalize things a bit. Okay, so let's do the problem.